welcome everyone to this video. Today I'm going to talk about a very important concept that is often overlooked by people learning about clustering when going through ML courses on Udemy, YouTube, whatever, which is how to handle mixed data types while clustering. Well, if you don't know about it, you can't just apply k-means clustering to a data set which has got mixed data types. By mixed data types, I mean categorical, ordinal, and numerical, all kinds of variables in it. And we need to figure out some kind of a solution to it. So we'll talk about one of those solutions today, which is using Gower's distance. How can we cluster a data set which has got different kinds of data types? So mixed data type is a pain point, as in, which is the most popular clustering algorithm that you know about. It's k-means clustering, right? Or k-modes clustering. So one thing is obvious, that real-world data sets will almost never contain only numerical columns, or only categorical columns, or only ordinal columns, right? They are obviously gonna be combination of all these three. Well, there can be some exceptions, like some financial data or something like that. But if you're talking like data about customers and you want to cluster them out, then obviously you'll have some sort of categorical information about them, like their gender, some ordinal information about them, like their education, and numerical information like revenue and all those things, right? And you want to use all of that as a contributor to your clustering algorithm. And common algorithms like k-means and k-modes cannot handle mixed data types because of the distance metric that they use. So k-means uses Euclidean distance, which is a distance between 2 points in a Cartesian space. So it's pretty obvious and pretty intuitive that distance between two categorical values like male and female does not make any sense when we use Euclidean distance, right? Similarly, k-modes algorithm cannot handle numerical values because k-modes uses some sort of distance metric which is only suited for categorical columns like Hamming distance. Well, if you want to know more about these distances, I can cover them up in more videos. Just put it down in the comment. So, as I said, the Euclidean distance between a male and female or any categorical values doesn't make sense. So what is the solution? The solution is using some sort of distance metric that can handle all these kinds of data types together so that we can analyze the entire data set for clustering. So there are multiple solutions for this. One of them is the k-prototypes clustering. I'll be covering it in a separate video. But today we're going to talk about Gower's distance-based clustering. So let's see what Gower's distance is. So Gower's distance is a distance metric which is designed specifically to point out dissimilarities or quantify dissimilarities between numerical column values, categorical column values, as well as ordinal column values, and normalize them all so that we can analyze them together without having to worry about the data type. So you can see this weird looking and quite complicated looking mathematical formula over here. Here dgij is the Gower's distance between two data points I and j. You can consider two data points to be two rows of data. So the Gower's distance between I and j is going to be the summation of wk dkij, where wk is the weight attached to the kth variable. So for example, if you have a variable, numerical variable revenue, then wk can be the weight which we want to attach to it. So if you want that the revenue should contribute more to the clustering than other columns, then we can attach it a higher weight, just like we do in, say, linear regression. You know about weights, right? So wk is the weight, and small dk ij is the distance, or we can say the dissimilarity So why am I using the word dissimilarity instead of distance? Because when I talk about categorical variables, distance really doesn't make a lot of literal sense, right? So if I'm saying that there is a lot of distance between male and female categories, that doesn't make sense, right? So it's better to use the word dissimilarity, that male and female are dissimilar in our data set, not in the social sense, maybe. Okay, coming back to this. So dissimilarity is more of a generic term that we can use to quantify the distance between the data points, okay? So small dkij is the dissimilarity between points I and j in the column k. And then we multiply wk and dk for every single column, and then we sum them up, and then we divide it by the sum of weights. So usually, the weight is going to be 1 for each column. The reason is very simple, that we want each column to contribute equally to the clustering. But if we want, then we can modify it if required, if we have a use case where we need to do that. So Gower's distance also balances the contribution of each variable by attaching weights to each. So we also have that, a wiggle room for customizing the distance metric if we want to lay emphasis more on a particular column. So even if you didn't get this mathematical thing which I showed here, we are going to have, in the next slides, we are going to cover kind of the practical use case where you can understand it in a better way. So what is the intuition behind Gower's distance? Gower's distance basically aims to normalize the dissimilarities between the data points in the numerical columns, the categorical columns, as well as the ordinal columns, so that we can look at the dissimilarity and we don't have to worry about which kind of column it belongs to. We can just look at a number and say that, okay, data points I and j are very dissimilar in revenue column and are quite similar in the education column, stuff like that, So it deals with numerical, categorical, and ordinal data types in different ways, and at the end of the day, it tries to provide a normalized or a standardized dissimilarity score for each one of them. So as you can see, for a numerical column, what it does is, if you have two data points, say I and j, then it just takes the absolute difference between the two numerical values. So for example, if we have the revenue column and the revenue is, say, for data point I it's 10,000 and for data point j is 20,000, then the absolute difference will be 10,000, right? 20,000 minus 10,000. So the dissimilarity in a numerical column between two data points I and j is simply calculated as the absolute difference between the values divided by the range of that numerical column. Range is simply the max minus the minimum, right? So this will result in a standardized dissimilarity score between two data points I and j in the numerical column k in the range 0 and 1. Similarly, for categorical columns, the dissimilarity score is very intuitive and very easy, that if the categories for data points I and j are same, then we attach a score 1. If it's different, we attach a score 0. So again, this is more discrete in nature, but again, it's a standardized score between 0 and 1. So it is comparable to numerical scores if you look at it that way. For ordinal columns, so if you don't know about ordinal columns are just kind of categorical columns, but they have a rank attached to them. So for example, education level, bachelor's, master's, PhD, all these are different categories, but they also have a rank attached to them, right? So a bachelor's can be rank 1, and then PhD needs to be at a higher rank of importance, right, in some way. So we need to quantify that as well. So those are called ordinal columns. And for ordinal columns, we ordinal encode them, and then we again treat it like a numerical column to get a standardized dissimilarity score. If you get confused a little bit here and there, don't worry, hold it. We're going to look at the hands-on part, and I'll make sure that you get it, okay? So moving on to the next slide. Here I'm trying to give you a practical understanding of how Gower's distance treats different columns and generates a standardized score, or the normalized score which I'm talking about. So here I've got a small data set with ID is the unique identifier of that particular data point, age is a numerical column, income is a numerical column, gender and owns house are categorical columns. Here we don't have an ordinal column, so don't worry about that. Here, when we are finding dissimilarity between rows A and B in the age column, which is a numerical column, we are just using the methodology which I talked about in the previous slide, which is the absolute difference between the two values divided by the range of that particular column. We got a value 0.5. Similarly, when talking about the dissimilarity between the same data points A and B in the categorical column gender, we can see that as the gender is different, so we just provide a value, 1 if male and female, those are two different categories, so we can just attach a value 1. And had they been similar, then we would have attached a value 0. That's intuitive. Maybe I made a mistake in the last slide. A dissimilarity of 0 means that they are the same, right? They are not dissimilar. So that's pretty intuitive if you think about it. Similarly for owns house, which is a categorical column, because the owns house category is yes and no for A and B. So we have a dissimilarity of 1, which means they are dissimilar. And similarly for income, which is a numerical column, we apply the same kind of method and we get a dissimilarity of 0.5. So here you can see that for each kind of data type, each kind of column, we have generated a dissimilarity between two data points A and B in a standardized format in a range of 0 to 1, so that we can compare them now. Moving on to the next slide. Okay, we got the distance or the dissimilarity between data points A and B for each of the column, but what is Gower's distance? To get the Gower's distance, we condense all of these dissimilarities of the different columns. In this case, because we have attached a weight of 1 to each one of them, so we don't need to worry about that. So in generic terms, we are taking an average of all of these dissimilarity between A and B in the different columns, and we simply get a score of 0.75. Here you can see the magic happening. We can easily take an average over here without worrying about the kind of data type that we dealt with, because we have normalized the dissimilarities, which is what Gower's distance is all about. So here we have got a Gower's distance between A and B of 0.75. So in the similar way, in Gower's distance method, we get pairwise distances between all the different data points. So we get a pairwise difference between, in this case, A and B, B and C, A and C, and then we can analyze which points are similar to each other and which points are highly dissimilar to each other using the Gower's distance. So you can easily understand now that because it is a pairwise metric, which is basically calculating the similarity for each column and then condensing it, it is quite computationally intensive. Therefore, you might want to weigh your options when using Gower's distance, because it takes time. Okay, it's not a very fast method. If you're dealing with a huge data set, you will take a lot of time to actually run this algorithm, because the time complexity is clearly quite high in this case. Now, once we get the pairwise distances between all the data points using the Gower's distance, we can generate the Gower's matrix. Gower's matrix is a condensed form or a condensed matrix, which is simply showing the quantified dissimilarities between the different rows or the different data points. So here, if we generate the Gower's matrix for the simple data set that I had, we get the Gower's matrix as shown here. Here you can see that the dissimilarity between row A and row A is 0, obviously, because they are the same, it's the same row, while the distance between the rows A and B is 0.75 as we calculated in the last slide, and similarly we get the dissimilarities for each one of them. Here we can easily see that row A and row B are more dissimilar as compared to row A and row C, which has a Gower's distance of 0.5. So this particular matrix is providing us information about the dissimilarity of each data point from each other data point, irrespective of the data type. So we have taken the data types part out of the question over here. We have kind of solved the problem. So this is what we wanted, right? Cool. Now let's get hands-on, and I'll take you through a simple use case of a simple dummy data that I generated, so you can understand how can you use Gower's distance for clustering. Let's get at it. I have created a Colab notebook. I'll be sharing with you the link to this or whatever. I'll maybe upload it in the GitHub. I don't know what I'm gonna do, but this is it. Okay, so first of all, I am installing these libraries, NumPy, Pandas. The Gower library is the one that we use for creating the Gower's metrics, using the Gower's distance and all those things. Scikit-learn, as we know, is kind of the mother of ML libraries. SciPy, Seaborn, okay, for visualization, Seaborn and SciPy. You might want to use SciPy as well as an alternative to Scikit-learn. Okay. So here, don't worry about this. I've just used ChatGPT to generate a simple kind of a dummy data set over here. And the data set looks like this. So we have got total 6 columns. Here, age, income are numerical columns. Education level is an ordinal column because not each category can be treated in a similar manner. Gender, marital status, car ownership are categorical columns. So this is kind of an umbrella case for dealing with mixed data types. Okay. So first of all, another question comes, should we scale the values or not? As we know that in k-means clustering, we need to scale the values because Euclidean distance is very much susceptible to the scale of the numerical values. But should we scale the values in this case, the numerical values? Or should we one-hot encode the categorical columns? The answer is no, because we see that in case of Gower's distance, it is already normalizing the dissimilarities by dividing each dissimilarity by the range of that particular column. So we don't need to care about scaling them up, okay? The only thing that we need to do in the form of pre-processing over here is ordinal encoding the education level. Because as I showed you over here, let me go back, yeah. For ordinal column, the values are treated as ranks, and then this similarity is calculated similar to numerical column. So we need to get these ranks, okay? So we need to ordinal encode it. We can use the ordinal encoder module from sklearn the pre-processing. And I have decided to give rank 1 to high school, 2 to bachelor, 3 to master, and then 4 to PhD. Then I transformed it, and here we have the transformed ordinal column, okay? So I can see that the first row was high school, which is 0 now. So now basically we have converted it into a kind of discrete numerical column, and we want Gower's distance to treat it like, I don't know, a numerical column. And the dissimilarity at the end of the day is gonna be a standardized score between 0 and 1. So now we have 2 numerical columns, age, income, 1 encoded ordinal column, education level, 3 categorical columns, gender, marital status, and car owner. Now let's get the Gower's metrics using the Gower library. So to get the Gower's distance now, after we have done the pre-processing, which was simply ordinal encoding the ordinal column, using the Gower library is pretty straightforward. As you can see, we import the Gower metrics module, and then we create a Gower matrix from our data frame. Here you can see that it is in the form of an array. Now looking at this array, it's pretty shabby, it's pretty confusing. So I have created a heat map for this. Yeah, this heat map is a little bit like, let me just open the image in a new tab. Yeah, I think I can access the tab over here. Yes, sir. Okay. So this is the Gower's matrix that we have. Luckily, in this case, the data set size is quite low. So our df dot shape, is it working? But yeah, our df dot shape shows that we just have 20 rows. Okay. So just because we just have 20 rows, so the Gower's matrix visualization is quite small, even though it looks large over here. But it's understandable, So here we can read it in this way, that the dissimilarity between row 0 and row 1 is 0.54. The dissimilarity between row 0 and row 2 is 0.14. Now, row 12 and row 19 are highly dissimilar. At the same time, let me see, yeah. At the same time, row 8 and row 2 are very much similar to each other because the dissimilarity looks very small. Let's look at it at a deeper level, okay? Let's visualize what does it mean to be similar and what does it mean to be dissimilar. So here I have identified that row 2 and row 8 look pretty close, which is row 2 and row 8, this one, yeah. It has a very low dissimilarity value, 0.011, or a very low Gower's distance between these two rows. And I have identified two rows which look extremely distant, which are row 12 and row 19. So row 19 and row 12. Yeah, it's like the perfect case. The dissimilarity is literally 1, which is the highest value that it can hold. Let's see what these rows have in them. So looking at row 2 and row 8 now, we got a very less amount of dissimilarity for these. So these two should be very close to each other. As we can see that the ordinal column is the same, all three categorical columns are the same, age and income are also almost similar with very less difference, so makes sense. Now looking at the extremely distant rows, row 12 and row 19, we can see that these two are pretty dissimilar. For all ordinal and categorical columns, the values are dissimilar. Income is literally miles apart. Age is also miles apart. Okay, so it makes sense. It means that these Gower distances are actually summarizing the distance between our data points pretty well. Now, we need to use this distance metric, the Gower's distance that we have calculated for each of the points, for each pair of points rather, for clustering these data points now. Now one thing, how should we cluster them? Okay. One option that we have at our disposal is k-means. That use k-means instead of Euclidean distance, use Gower's distance, but that won't make sense. We can't use k-means over here because k-means requires us to calculate the centroids, which is the mean of all distances, which doesn't make sense when we are dealing with categorical variables. Because that centroid method, the entire k-means algorithm is built around Euclidean distance. So finding centroid of a categorical value doesn't make sense because it doesn't exist, right? There is no centroid. There is no mean between two categories like male and female. It just doesn't exist. So when using Gower's distance, we need to go for hierarchical clustering, or we call it also agglomerative hierarchical clustering. You can read about that if you don't know about hierarchical clustering a lot. Put it down in the comments if you want a similar kind of a detailed video on it. Cool. So we'll be using the sklearn library and we will be implementing hierarchical clustering using the Gower's distance. Then we are going to use silhouette scores for finding optimal number of clusters. And in case you don't know about silhouette score, I recommend reading about it, but I have provided a small explanation over here in case some dude is wondering what is silhouette score and why are we using silhouette score over here. If you are into clustering, k-means clustering, you must be knowing about the elbow method, right? But elbow method is a method which is based on within cluster sum of squares, which is again a Euclidean distance based metric, so we can't use that over here. We are going to use silhouette score over here. Silhouette score, or this silhouette coefficient, is basically the similarity of a data point within its cluster, which is called as cohesion, compared to other clusters' separation. Think about this. We have two clusters. Say that we have these two clusters. When I pick a point in this cluster, I want the average distance of this point to all the points in its cluster to be very low, because it would mean that our clusters are compact in nature. And I want the distance between any point in this cluster and any point in another cluster to be very high, which would mean that our clusters are quite distant from each other, which basically can be visualized as a good cluster, good clustering. Okay, there are exceptions in this as well. There are some weaknesses of silhouette coefficient as well. You might want to read about it, research on your own. But yeah, so the distance, the average distance of this data point to all the data points in the same cluster is called as cohesion, and the average distance of a particular data point to all the data points in a different cluster, to points of different cluster or neighboring cluster, is called as separation. We want ideally the cohesion to be small and the separation to be high. Okay, so for each data point we calculate the silhouette coefficient as bi minus ai divided by max of ai bi. Ai is cohesion, bi is separation. So look at it and you can understand that because it is being divided by the max of both, so the value is going to lie between -1 and 1, and it's going to be a normalized value. And as I said that I want the cohesion to be very small and I want the separation to be very high, so the ideal value for SI, or silhouette coefficient, for a data point would be 1. And if the value is 0 for the silhouette coefficient, then it would mean that the cohesion and separation are pretty much similar, which basically means we are having overlapping clusters, not a good thing to have. And if we have the value as -1, which basically means that the separation is very, very low as compared to the cohesion, which basically means that our clustering is rubbish. It doesn't make any sense, okay? It's the worst kind of clustering that you can have. So we are going to select the number of clusters which gives us the highest amount of silhouette score. Okay, cool. Highest value being 1. Okay, so here I have defined that, okay, I am going to do the analysis between, let me zoom out a little bit more. I'm going to consider number of clusters between 2 and 11, and I'm going to calculate silhouette scores for each one of them. I'm looping on each of these number of clusters, clustering them using the agglomerative clustering module of sklearn. Here the number of clusters is number of clusters. Metric is pre-computed. What is pre-computed? So by default, hierarchical clustering uses a distance matrix. So I could have wrote here Euclidean if I wanted the hierarchical clustering to be based on Euclidean distances. It would create a Euclidean distance matrix. But because I already have a distance matrix, which is the Gower's matrix, so I am entering pre-computed over here as a metric. And linkage is going to be average. If you don't know about linkage, I'll talk about it in a while, okay? Let me just finish this up. And then for those who are a little bit more enthusiastic, okay, I love you guys, by the way. And I'll be talking about it a little bit, and I'll be sharing a link as well if you want to learn more about it. So it's basically a very fundamental concept of hierarchical clustering. Then we get the cluster labels for them by fitting and predicting using the Gower's matrix. And then we get the average silhouette score, or the average silhouette coefficient for a particular number of clusters. And then we just input that particular silhouette score for that number of cluster into the silhouette score dictionary over here. You can play around with this code, okay? And the optimal cluster obviously will be given by the number of cluster for which the silhouette score is the maximum, because that's what we want. We want our max silhouette score, which is nearer to 1, okay? So here I'm getting optimal cluster as 7, okay? Let me also print the silhouette scores, okay? The dictionary silhouette scores. Let me print both of it for clarity. As you can see that we got a silhouette score for each one of them. So for 3 clusters, we got it as 0.68, 64, 74, all these things. And the maximum silhouette score was obtained for 7 number of clusters, okay? Well, it looks pretty competitive out here. Don't judge this because, you know, it's fabricated data, it's a dummy data, okay? If you want me to kind of talk about or provide a hands-on session using a real-world data set, it'll be like a 1-hour project kind of a thing where we do pre-processing and everything. Just put it in the comments because I want to understand if there is an audience for that sort of detailed content, you know. Cool. Then we can just visualize the silhouette score. So here we can see, let me zoom out a little bit, that the silhouette score is maximum for 7 number of clusters. Let me also switch on the grid, okay, so we can look at it in a better way. Why is Google Colab so slow, man? Cool. So the max silhouette score we get for 7 number of clusters, so we go forward with 7 as the optimal number of clusters. Then I fit the agglomerative clustering model again, this time using optimal clusters, which is 7. Again, metric is pre-computed, linkage is average, and we get the cluster labels and we attach that cluster labels as a new column in our data frame. Now we looked at, if you remember, we were analyzing these 2 cases, right? Where row 2 and row 8 were pretty close, and row 12 and row 19 were extremely distant as per the Gower's matrix. My bad. Now, to kind of confirm that our clustering really worked, we would ideally want that these 2 data points, as they are pretty close to each other, these should be in the same cluster, and these 2 data points, as they are very distant from each other, these 2 must be in a separate cluster. Now let's see if that has happened. Again, looking at row 2 and row 8, you can see that these 2 are assigned the same cluster, well and good. And then row 12 and 19 have been assigned a different cluster. So it basically means that our clustering thing has worked. Now, so in this way, you can deal with mixed data types. This is one of the methods that you can use. There are other methods like K-prototypes as well. And you can also frame your own custom method if you want, if you have a niche use case, okay? So this was it. This was about Gower's distance. And comment out if you want something else, something specific, okay? And as promised, let me just show you a little bit about linkages. This is a link I got that talks about what are linkages in clustering. So linkages is nothing, but it's a method of finding the distance between 2 clusters while doing agglomerative clustering or hierarchical clustering, okay? So think about it. You have 2 clusters. This one has 5 points, this one has 5 points again. How do you calculate the distance between both of these? Now here we are not using any centroids, right? We used to do that in k-means. So there are multiple methods of doing it. First is the single linkage method. What it does is it considers the minimum distance between any 2 points of these 2 clusters to be the distance between these 2 clusters. In complete linkage, we consider the max distance between any 2 data points of these 2 clusters to be the distance between these 2 clusters. The average linkage, which we used in our use case, it basically calculates the distance between each data point with each data point of the different cluster and then averages it out, and then we get a average distance which is taken to be the distance between these 2 clusters. As you can see over here, average linkage is kind of a better approach, which is combining the flavors of single linkage, complete linkage, and apart from these 3, it's not given over here, but apart from these 3, there are other methods as well of linkages and all these things. Depends on the use case. So yeah, I'll be sharing this link as well if you want to take a look. So this is it, guys. I hope I covered literally a lot of concepts that will help you be a better contributor to whatever you're doing in the future. So thanks for watching. Bye-bye.